Hello everyone! Our final talk of OmniTestingConf is going to look into the future of testing. Our speaker in this session is Jeremias Rößler, who is the CEO and founder of Retest. His talk, How to Bring AI to Testing, will introduce you to the many ways that AI can be applied to QA, like generating fixes for code, for example. As you already know, you can ask questions through the Ask a Question button, and after the presentation, we'll have a 10-minute Q&A where Jeremias will answer your questions. Now, I'm going to hand it over to Jeremias.
Hi, and welcome to my talk about how to bring AI to testing. My name is Jeremias Rößler, and if you want to know more about me, you can find that online. So, AI. As you know, AI has been a buzz recently, and the reason is that it transformed from. There's been quite a few achievements from IBM Deep Blue, where they were able to beat the Grandmaster in chess, to IBM Watson, where they were able to beat the Grandmasters of Jeopardy, to AlphaGo, where they were able to beat the Grandmaster of Go. And with that, it came to media and public attention that AI has quite a few very powerful, very potential features going, and that it's evolved from being a quirky little research pet project to something that's actually quite powerful and can be applied to a wide variety of problems. One of those problems is testing, because as some surveys found out, testing is right now the bottleneck in software development. And 99% of companies face challenges in testing, most of all in an agile environment. Then it's only natural to assume that if we have this very powerful, very new and shiny technology that is AI, to apply it to testing and solve testing with that, right? Okay, let's see. How could that work out? So you, as a human, if I ask you, test this software and tell me whether that value is correct or not, you had actually quite a hard time doing so, right? Because you don't know the software, you don't know the data, you don't know the configuration, you don't know what it's for, or what that value even means. So you have no way of deciding whether that value is correct or not. And quite frankly, AI is in the exact same situation. This is, by the way, called the Oracle problem. And the reason why it's called the Oracle problem is that for AI, or actually any given entity, to be able to determine for any given software whether it's correct or not, it would have been able to answer all questions. Because I could write a 3-line program and then simply that maybe always returns no, and just ask it, does God exist? And then, for the given answer, which would be no, in order to determine whether the software is correct or not, it would have been the entity that I'm referring to, that tests my software, would have been to be virtually an oracle. And turns out you can turn any given question, any given problem, into the oracle problem. So now, if you're a tester, you can now go to your boss and ask for a raise, because every day you try to solve the most difficult problem of humanity. But maybe I don't want to address problems like, does God exist? Maybe I just want to answer, is it value correct or not? But still, that is a very hard problem. And maybe it's not even the right approach. Maybe that's not even the best way to go. So let's see. Like over 100 years ago, the steam engine was invented. And at the time, people wanted to apply it to, or combine it with a buggy, to have some like mobile steam engine and increase the mobility. Now, if you do this in a naive way, without thinking very hard, what you could come up with as a solution would be something like the mechanical steam engine powered horse, right? So this is a way you could just replace the natural horse, the animal, with a mechanical horse and be done with it. However, as you all know, this is not what happened, because coming up with such a mechanical horse is quite hard and would be even hard today. So instead, what they did is they invented the steam locomotive, right? They put it on wheels, and those wheels they put on railway tracks. Now, in order for the locomotive to work, to be able to use it correctly, you have to build railway tracks. And especially in a country as big as the US, this is a huge effort. But as you all know, they did that and it paid out in the long run. Maybe we need to do something in software development just the same. Maybe we need to find a way to apply that new and powerful, shiny technology, which is AI, to our problem. So we can't just replace the manual tester with AI, just as we can't replace the horse with a mechanical horse. That's just not the way it works. So maybe let's go to our overall process and see what can be done. So this is a schematic abstraction of a software development process. So maybe you start with ticket systems, where you have tickets both of bugs and features that feed into the development lifecycle, where developers push out changes to, say, a testing stage, and there you either have manual tests or automated tests, or maybe both. And from there, depending when the quality is good enough, at some point you release to production. From production, there's maybe test data that is fed back into the testing stage, and both from manual testing, automated testing, and from production, you have tickets, again, which are bugs or feature requests that feed into the ticket system, which again feeds into the software development lifecycle. So this is a fairly, I would argument, a fairly typical abstraction of how a software development cycle could look like. Now, if you think about AI, there's quite a few things you can do with AI to help improve the efficiency of that overall cycle. So, for instance, in a ticket system, you could use AI for bug triaging. If you're a big company like Facebook, Google, or the like, up to 25% of your tickets are duplicates. Think about that. How much effort, how much manual effort is needed in order to identify these duplicates and remove them? Then if you have a failing test case where you can just use that you can execute in order to pinpoint, say, maybe a technical issue, maybe a null pointer exception or something like that, then you can use AI to come up with defect analysis. So you can pinpoint developers to problems saying, oh, this null pointer exception, for instance, is probably related to this data point or to this erroneous transaction, to this, database problem, whatever. Then, at some point, the changes that are pushed from development to testing and production, those can be analyzed by AI for anomalies. So you can say, oh, these are typical changes, and this is something that is maybe fraudulent, maybe something that is high risk. So let's have a closer look at that. Let's flag it and have someone else take a second look and see what's going on here. It's fishy maybe. Then before we do an actual release, we can use AI to do risk prediction. As has been proved in the research, for instance with Eclipse, they found that if you make changes to the UI, those changes tend to be much less risky than if you make changes to the core, to the underlying compiler, for instance. So you can assess changes and classify them according to risk, and again go and say, oh, this is a very risky change, maybe we should have a second look at that. Another very widespread problem is that you don't have test data available in your testing stage as you would like it. You could use actually AI for test data generation. A very illustrative example is, for instance, if you go to the domain thispersondoesn'texist.com and generate images of people that don't really exist. Now think about that. if you can use AI to generate images of faces, of human faces that are in a way not easily separatable from actual humans, then it's clear that you can generate almost any kind of test data with AI. So this is another very big field where AI can be applied. Then if you have a lot of tests, if you think about thousands of tests, then it's essential to, maybe you don't want to execute all of those tests all of the time. Maybe you want to just execute the tests that are relevant for the changes being made. So you can use AI for test selection. And again, this is correlated with risk prediction, so that you see which changes have a higher risk of being faulty. And the last piece of the puzzle is test generation, optimization, and maintenance. And this is actually very closely related to our initial problem. So if we can test a system using AI, then we can generate tests. And if we can generate tests, then where's the difference between test generation and actual testing, right? So let's go into that into more detail. So with those changes, or with those insights, the question changes from how do you bring AI into testing to how do you bring AI into test automation. Now, if you think about test automation, there is a difference between executing an automated test and doing manual testing of the application. If you do a manual test, you look out for anything that's not quite right. You challenge assumptions, you do maybe exploratory testing, and you try to come up with things that don't feel right or with outright bugs. With test automation, however, it tends to be that if there's something been like that for the last year, you just assume it's correct, right? So you don't challenge the status quo. So if something didn't change, it's probably correct. And that's exactly the difference. So in our opinion, automated tests are not really tests, because automated tests don't challenge the status quo. Automated tests just look for changes. And we already have systems that do that. We call them version control systems. So in a way, an automated test is actually version control, because you don't look for the correctness of the software, you just look for changes, right? However, the problem is that current version control systems don't gather every aspect of the software. Version control systems, as they are today, only care for static artifacts, files, code, configuration, stuff like that. However, we all know that software is more than that. Software is comprised of the code, but also of the runtime system and the data. So the dynamic behavior of the software is determined by more than the code, and therefore all of those aspects that are not governed by current version control systems are being lost. What we do is we use automated tests to close that gap. So in that sense, an automated test is just a way to turn the dynamic runtime behavior of the software into an automated tests to be able to govern that automated test, that script, which again is code and static artifact, again with version control system. But if you think about tests like that, then they are a crutch. They don't address the problem properly. They are just doing it in a way, okay? We think that we can do better. And other people have suggested that idea as well. The idea is that you don't define the outcome in terms of, like, say, an assert, but you approve it, all of it. So first you test manually, ensure that everything is as you want it, and then the system makes sure that it doesn't change involuntarily in a way that you don't want. This kind of testing is called golden master testing, and it's been around for quite some time already, and there are a couple of even open source products that you can use, for instance, approval tests. So the idea is when you run the test the first time, the output is persisted as a file, as a static artifact, and the next time that the same test is executed, the system approval test, for instance, just makes sure that the output is just the same as it was before, and any change is being reported and makes the test fail. Then you, as a developer or tester, can decide whether this is an intended change of the system, and you approve the change, updating the baseline or the golden master, or you found a test. You found a bug. If you think about it, classical tools like Selenium and others have a deny listing approach to changes, because, as I just said, one of the outcomes could be that it's an intended change and then you want to update what is being checked, right? So it doesn't mean that automatically the test is correct. So you have changes, and if you write an assertion with a traditional JUnit style approach, you deny that change from happening without you being notified about it. So in a way, it's a deny list of changes. If you think about Git, for instance, then it's the opposite. With Git, you are notified about every change, and then you can decide whether you want to ignore it in the future. So you maintain a ignore list of changes with a git ignore file, for instance. So this is, the version control approach. So this is the spectrum that you have. If you have no git ignore file, or no ignore file for the golden master, then you check everything. If you have an assert or a deny list of changes, or if you don't have any assertions, for instance, then you check nothing, right? Usually the ideal amount of checks is somewhere in between. Now the question is, how do you approach that? How do you get to that ideal amount of checks? And what is better? What is the least amount of effort? And what is the safer thing to do? Now think about unexpected changes. For instance, Google, I didn't know that, but Google apparently has a way to mark things that have been changed for testers, so they can scrutinize that and very intensely test it. So in that situation, for instance, that combo box is marked with a dancing unicorn, and you as a human tester know that this has been recently changed and can go for it and test the hell out of that. However, at some point, these marks, the unicorns, weren't removed, meaning that the customers had suddenly dancing unicorns on their screen. Apparently, nobody thought of writing an automated test that makes sure that there are no dancing unicorns on the screen. Obviously, a first thing to do, right? So the thing is that with a deny list of changes, you can only deny what you can think of. Unexpected changes go unchecked. With an ignore list, you get notified about every change, and then you can decide whether you want to ignore it in the future. So any unexpected change, you will be reported. And this is also the reason why if you implement, say, a firewall, you want to go with an ignore list, whitelist of things that are allowed, because then unexpected things are brought to your attention. The second aspect is, what's the ideal amount of checks? Well, in our experience, you probably want to check more rather than less. So you start with checking everything, and then you just ignore what you don't care about. Actually, we implemented an approach like that. We called it recheck, and for web, recheck web. You can go to GitHub and download it and use it in your own tools for free because it's open source if you implement or if you work with web applications. We call it internally, we call it Git for the GUI because it works just like Git. And like Git has a git ignore file where you can ignore files that are irrelevant for you. The same is true for retest. So we have a recheck ignore file where you can ignore every aspect that you don't care about, that is irrelevant to you. And you can use that and utilize that to ignore, for instance, the font but not the text, or vice versa. Ignore just the layout but not the contents, or just the contents but not the layout, or any other aspect. Mix and mingle as you wanna, as you like. So it's a very powerful tool, and I encourage you to go there and check it out. But the thing is, why we implemented this in the first place is because it then enables test generation. As I said earlier, the real problem with testing and test automation, or the generation of automated tests, is the Oracle problem. With that approach, we can circumvent the Oracle problem, because we can then just look for changes, which means that now we can, because the complexity of the software is, in an ideal world, is hidden away, and from a tester's perspective, you just have the easy to use user interface. Again, in an ideal world, the AI can then just use the UI to generate tests. With the Oracle problem out of the way, this is what we can do. Actually, we don't even need AI for that. As of the infinite monkey theorem that says a monkey hitting keys on a random on a typewriter for a long enough time will eventually type all the complete works of William Shakespeare, same is true for AI testing a application. So we just replace the typewriter with a computer and have the monkey test the application. So in eternity, the monkey will come up with perfect tests for your application. Problem is just, that it takes eternally long for him to do so. So then we can use AI and make the monkey more intelligent, like so, and have the monkey come up with great tests for your application. So we use two different versions of AI. We combine artificial neural networks with genetic algorithms. The problem with artificial neural networks is that you need a lot of test data to train them. And not for every project, like if you're on Google or Amazon, this is probably not the right approach for you. However, what we did is we trained the AI, we trained the neural network, how a typical user uses typical software. So it's not, the network is not trained specifically for your application, but for software in general. I'll come to that in a second. And then we combine it with a genetic algorithm that you can give your specific test data to. And the nice thing about that is that the genetic algorithm has not, only uses a couple of training tests, a couple of test recordings in order to be trained correctly. So you don't need lots and lots of training data. So what do we mean when we say we train how a typical user uses a typical software? Well, if you have a look at that e-commerce website, for instance, what you can see here is that all the elements that the user can interact with are being rated. And what is highlighted here is what the AI thinks is the user interface element that has the highest probability for the user to interact with it. So if we click on it, we come to that next site where you can add that item to the cart. And as you can see, again, that button where you add it actually to the cart is the most prominent one, the most in the center, the most highlighted one, the most distinct one, and the AI takes up on that. So the AI can get the nudges on how you try to nudge your users into doing specific things. The AI can take up on that and can learn how to use your specific software. So it won't click on, say, the currency, or with a very low probability will click on the currency, and with a much higher probability will add that item to the cart. If you follow that, then the proceed to checkout again has the highest rating. So, and again, proceed to checkout has the highest rating. So overall, it will just, with learning how a typical user uses a typical software, it will, in that scenario, first thing it generates is the use case of actually going through the checkout and ordering something from your web shop. So this is how we trained the AI, and you get that without any additional training. So the only thing that you would need to give it in that scenario is a valid username, a valid password, and maybe a credit card, depending on whether that's already being entered into the system or not. So you have to give it very, very few things to work with, and the AI will come up with a lot of additional scenarios that just feel right from a user perspective, because this is what a typical user will do in that situation. Actually, we're not the first to come up with the idea. Sapiens from Facebook has something similar, where if you're a developer at Facebook, that software Sapiens will generate a lot of test scenarios for your mobile application. So overall, I am thinking back about the mechanical horse, the way that the software development process needs to change in that scenario is that you start with a manual test where you test a specific version of the software, and while doing so, you can actually already train the AI, which then will automate the test for you, come up with test automation in that case, and then after a change, this change will be highlighted, and the user only needs to approve that change and have a look at that. So another aspect that has been highlighted previously is how do you bring AI into testing? Instead, we want to answer how do you bring AI into test maintenance? So how do you maintain those tests? And people have been talking about self-healing capabilities of tests using AI. So how does this work? Well, the way we implemented this is that if the typical test that you execute can't find a specific element, say the login button, what we did with the golden master approach is we have a copy of the website. So if something changed, the ID, the text, the XPath, whatever, we still have a copy of the website, an old version where we can find that element. Then we just need to make a one-on-one assignment of the old version to the new version, which we need to do anyway in order to pinpoint the changes. And then we can find the element with the highest overlap, the highest match, return that, and the test doesn't even break. Then you can use that information to apply it both to the golden master and to the code, and thus auto-heal the test. And you know what? You don't even need AI for that, as you see it here. The next step is going from automatically healing the test cases to automatically fixing the bugs. And this is something that has already been implemented at Facebook with SAPFix. However, unfortunately, this is not publicly available. The idea being that if you have a simple technical problem, like a null pointer exception, array index out of bounds exception, stuff like that, then you can generate test cases to trigger that. And with, in such situations, you often have a simple fix, which is check for null, for instance. And then you can generate that fix, and having all of those generated tests can make sure that you don't break existing functionality. Now, the time is up. I need to wrap up. And I want to end with what I showed to you today is only the beginning. If you think about how the web started and what way we've come until today, it's a long way, right? The web has developed tremendously from the early beginnings to what we have today, and the same will be true for AI. So this, what you see here, is essentially what AI today is the current status that AI is in. It's the new thing. There are many things we need to learn, many things we need to solve, still problems and challenges that we need to address in order to leverage it correctly. But I think it can be done. So thanks for your time. Thanks for listening. And now, do you have any questions?